Mathematica and the Raspberry Pi. Array factor. An object that radiates energy equally in all directions is called isotropic. If a series of these are placed in a straight line, the overall radiation pattern changes as a function of a number of variables such as the number of radiators, the distance and signal phase shift between them, and so on. The result is called the array factor. On a linear plot, it resembles this. Adding the manipulate function allows us to see how the overall radiation pattern changes by varying some basic array characteristics. Since isotropic radiators are assumed, this effect will alter the radiation pattern of any antenna array, regardless of the pattern of individual radiators. The polar plot makes it much easier to visualize what is happening. If the energy is radiated perpendicular to the array axis, it is operating as a broadside radiator. However, it is possible to vary the basic parameters such that the bulk of the energy comes in line with the array axis. This is called the end fire mode. Notice also that the main lobe can be directed to any angle between the two modes. This forms the basis of the phased array or scanning antenna. And because of the symmetry around the array axis, Mathematica can plot a 3D representation of the radiation pattern. The most common radiator is the half-wave dipole. We often see them stacked end-to-end vertically in a collinear dipole array. The individual radiation pattern of each dipole looks very much like a donut. We can now use the array factor to modify the radiation pattern of the half-wave dipole. In this plot, we see how the array factor significantly alters the radiation pattern of the dipole. If we examine the polar plot, we'll notice that all of the signal energy is broadcast perpendicular to the array axis, and none comes off the end of the array. Putting it all together, we get the 3D plot.